Hello and welcome. I want to welcome you all to our webinar on building successful vibration fixtures for electrodynamic shakers. My name is Mark Pike and I'm the marketing manager at Thermotron, and our presenter today is Milt Voss, a mechanical engineer at Thermotron. We are very excited to have you and we hope that you enjoyed today's webinar. Before we get started, I wanted to let you know that we will be muting everybody during the webinar, but we will still be taking questions throughout, so feel free to send them directly to the chat window on the GoToTraining panel, and you can send them to our organizer, Jane Newton. At the end of the presentation, Milt will answer some of the questions that were submitted. All right, well, let's get started. I'm going to hand it over to Milt, and he'll take it from here. Thanks.
Thank you, Mark. As Mark said, I'm a mechanical engineer with Thermotron Industries. I've got about 19 years of experience here at Thermotron with vibration. Almost all of my career here has been electrodynamic shakers. And as a company, we have gotten more and more involved in fixturing over the last number of years. So that fixturing has become a focus of our design and a focus of some of the things that we are concerned about. So we wanted to make sure that we could explain some fixturing. This presentation is a duplicate of a presentation that was presented to STEC back in May about fixturing. The things that will not be identical are your questions, so make sure you ask whatever questions you want. When we were talking about fixturing for ED shakers, the first things we need to talk about are these three items. We need to define what fixturing is. We need to talk about what we expect fixtures to do, and then we need to talk about how we design to meet those expectations. Fixturing defined for an ED shaker means it has to do two things physically. It has to hold the unit that's under test, or the UUT, and it has to attach to the shaker. It can possibly provide auxiliary functions such as cooling, heating, electrical power, fluid flow, and other items. Sometimes there's some digital information that has to be passed through the fixture. Whatever is necessary, that's the auxiliary function. Those are all niceties, but the number one thing that fixture has to do is it has to transmit vibration from the shaker to the unit under test. That is always in our mind when we're designing fixtures here at Thermotron, the most important function and expectation that a fixture can have. So when we're looking at the expectations, there are some things that we need to do to get those expectations solved. Number one, the unit under test has to be held securely, and it doesn't rattle or impact the fixture. Again, in the same way, the fixture attachment to the shaker has to be secure, and it cannot rattle or impact the shaker. So we have two things that have to be secure and have to be designed properly so that there is not rattling or impacting. If there is rattling or impacting, we get what are called nonlinear behaviors, and if those are bad enough, the shaker cannot be controlled properly. One of the things that we also look at is that fixture needs to be flat. We say 1/1000th of an inch per foot, and we use that because almost any machine shop that's capable of doing a decent job of machining should be able to get something flat within 1/1000th of an inch per foot. The other thing that the fixture cannot do is it can't stress the shaker table, and it can't have gaps at attachment points. Now, going along with that, not only can it not have gaps at attachment points, it really needs to be attached at every possible attachment point that's on the shaker. So if you have a standoff on the shaker table head, you need to have something that attaches to that standoff. It is not considered appropriate to simply have something jumping over top of those attachment points and letting those be free to rattle or buzz. Then another item that we're concerned about always when we're designing is that the fixture must be very durable, and for lack of a better term, we say hefty and strong. The fixture cannot have internal joints that rattle or impact in the frequency range of the test. That means that we want to eliminate bolted joints because that's exactly what they do. They rattle or impact in the frequency range of the test. It is very, very difficult to get a bolted together fixture to behave appropriately in every condition. Sometimes it's possible to get it to behave well in one or two tests, but for every possible condition you might want to put to it, it's going to be a difficult thing to do. That will become more and more difficult to control as your test becomes in frequency ranges that are higher in frequency, including shock pulses that are narrower in shock pulse. Those are equivalently the same thing. So when frequency ranges are too high, rattling and impacting actually affects the frequency range that can be driven through the fixture. Now, having said all that, I want to give you an example of a beautiful nonlinear fixture that actually does work. This is a fixture that a customer of ours produced. Was not produced at Thermotron, but it is a Thermotron customer. This fixture breaks all the rules, in my opinion, but it still was successful for this customer. And that's one of the things that we try to also look at is what is it that you're really trying to accomplish with your fixture. Once we know that, we can determine just how expensive that fixture has to be and just what you're trying to accomplish with it. So this fixture has hollow structural members, and those structural members are those long, long beams that run from front to back. Those are hollow aluminum tubes. It's got a fairly thin plate that's bolted down to the head of the shaker armature. It also has skip welds so that it's not solid welded. It has areas where the adjoining plates can buzz and rattle. And it has some pretty small attachment points where the product itself is attached to the fixture if you look at the end of the product. Those are actually very small screws that just are attaching. You can see it in the end view that we've got off to the right-hand side of this screen. So this fixture, even though I wouldn't have designed it this way, once I understood what this customer wanted to do, because he was running to very low frequencies and because this unit under test was extremely light, this fixture served his needs. So I want to kind of throw that out there right away as all right, I'm going to talk about a lot of fixtures that are very well built, very strong, very sturdy, but there's always a reason to not go down that road. And you as a customer and we as a designer have to share information so that we can get to you a fixture that is serviceable for your needs. What are the things that create nonlinear issues in fixturings? Any impact creates nonlinear behavior. That's the first item that we have to always attack, is any impact within that fixture itself. So if we have two surfaces that are joined, if those surfaces have the ability to pull away from each other and come back together and bang, and that is actually quite easy to do at higher frequencies, you will have a nonlinear behavior. In addition to impacts, there are certain modes of vibration that can become nonlinear. It's often called self-stiffening, or there's another term that's used called oil canning, in which as something bends, if it's a large enough item, if it bends in one direction, it stiffens it and suddenly it snaps and bends in a different direction. And that becomes a nonlinear issue too. So those kinds of things have to be looked at a little bit when you're designing a fixture. Another thing that causes nonlinear behavior is frictional contact or rubbing. This can really become a problem when you have a fixture that has a vertical seam in it. You cannot drive energy very well through a vertical seam because it's all dependent on friction. And at high frequencies, that frictional contact basically becomes no contact at all. And you cannot transmit any vibration through it. In addition to those nonlinearities that I've already talked about that are physical design criteria, sometimes fixture material selection and construction have direct impacts on linearity. There are times when we believe it's best to use one solid casting or one solid block of material and carve the fixture out of that because we've gotten rid of every joint that we could possibly get rid of. We also want to look at materials that are properly selected for fixtures, and I'll get into that in a little bit, but that's thrown up here now because it also can have effect on linearity. What do I mean by linearity? By linearity, I mean that for every input, a predictable and scalable response is achieved. That means that if I double the force that I'm trying to push through that fixture, the outcome at the other end of the fixture should double as well. Now that doesn't mean that at every frequency everything is identically the same, but it does mean that I have to be able to predict how much actually goes through. I have to know that, and I have to be able to scale that. If I can't do that, then I'm going to have a nonlinear fixture. When I have a nonlinear fixture, its response results in control as very difficult or maybe even not achievable at all. The bottom line is a extremely bad fixture can result in a destroyed shaker because the energy simply cannot get put into the fixture and can't get to the product, and the shaker can't make up an infinite requirement for energy. Fixturing quality, in this slide, I'm not talking about the quality of a vibration, so I'm not talking about Q, I'm talking about what I consider to be a well-made item, something of that quality. I wanted to make a statement there because I have had this confused with the Q of a fixture, the vibration response behavior. That's not what I'm talking about here. But when I look at fixture quality, I look at these items on this slide. The first thing I want to do on a fixture is I want to make sure that its center of gravity of the entire vibrating system must be on the center line motion. That center line has to add up completely so that shaker, armature, fixture, and unit under test must all come out so that the center of gravity is directly over the center of the shaker head. If that doesn't happen, you're going to get a rolling motion imparted, and now you're going to have another issue. The other thing that we'd like to look at in fixture quality are composites and dead material. Composites are phenolics. You can even create a fixture out of a marine plywood. It really isn't necessary to do a fixture out of metal, especially as your frequencies are low. But what we don't want to do is we don't want to use materials like steel and beryllium because they ring and they cause all kinds of other issues in the test quality. We have to remember that fixture resonances, which are natural, they're going to be linear to shaker input. At least we hope we are when we design a good quality fixture. Because if we can get that resonance linear to shaker input, we have a very good chance of controlling it. We might have to average in two different spots, but at least we can get those resonances to remain in a behavior that we can expect to have and that we can control. The other thing we want to look at for fixture quality is we want to eliminate joints, or at least we want to minimize them. Now, unfortunately, there's going to be two joints already. You have to have a joint between the fixture and the shaker, and you have to have a joint between the fixture and the unit under test. So we've already got two joints that we have to drive energy through. Adding additional joints is simply a recipe for disaster, and we want to try and eliminate them if possible, or at least minimize them. And again, like I said previously, test results and shaker life require quality in your fixture. This is an example of a very robust fixture with extremely heavy, or as I said earlier, I used the word hefty, construction in it. The center of gravity of this product, if you look in the left-hand view, you will see an eye bolt in the very top of the fixture. That is actually the center of gravity of the fixture after the product is on. That center of gravity is on the center standoff of the shaker. and that center standoff is just barely accessible underneath that center post of that fixture. What we ended up doing is on this particular fixture, we actually relieved the bottom of the fixture because we couldn't get at that standoff, and we just relieved it, and we made it even stronger so that nothing could bend about that. But you can see that on that base plate of that fixture, there's in the powder coated view to the right hand side, there's a number of holes in it. This fixture goes on a 24-inch armature and attaches to every hole on that 24-inch armature that it rests on. There are a couple of armature holes that are not used, but the fixture does not contact them, and therefore we don't have to worry about them. The blocks of magnesium in here are as heavy as 6 inches thick. The center post is highly machined. The product literally attaches to this fixture exactly like it attaches in its final use configuration. That's another thing that whenever possible we try to replicate, and we suggest that you, if in your fixture design, do the same thing. This was a very, very difficult project to machine because it had multiple planes. It was a very, very difficult project to even conceive of. The product literally slides in and out of the fixture and occupies places in space that we didn't expect it to occupy at first. The center of gravity calculation was very, very difficult to achieve. But when the fixture was finally completed, it was very, very successful. And if I have my information correct, by the time the fixture had been used on 3 products, it had paid for itself. This was not a cheap fixture, but it was extremely successful. And it has been purchased again for another project with the same product or a very similar product by this particular customer. So how do we go about designing good fixtures? Well, there's 2 approaches that I use. Either start from the top and work down, in other words, start from your product and work toward the shaker, or bottom up, start from the shaker and work toward your product. Those are really the only 2 ways of looking at it. What we want to do if we do a top-down design, we want to actually, in space, theoretically, we want to just take that unit under test and surround it with a solid mass, and then expand that mass downward to meet the shaker table. The bottom-up design does virtually the same thing, but in the bottom-up design, we can start out with plates, and then we just add material everywhere to prevent all these undesirable bending modes that are going to cause problems. Both methods assume that mass and volume, in other words, fixture mass and fixture volume, exist wherever it's possible. And here's the bottom line that makes fixture design so difficult. When you're reducing mass and you're reducing volume, you typically are reducing fixture quality. I'm going to repeat that because that's an important item to look at. If you try to make your fixture too light or too easy to make or too cheap, or maybe I should use the word inexpensive because cheap and inexpensive aren't necessarily the same thing, you will typically reduce the quality of your fixture. If you understand that, and if you are a customer like we had in that first set of slides I showed you, those first set of photographs, that's fine as long as you understand that. But if you are looking at that and going, well, why doesn't my fixture work, when you've already done all of the things that you shouldn't have done, it's time to step back and redesign and think carefully. This is another example of an extremely heavy fixture. The customer insisted that this fixture be mounted at the 2 gimbal points that you can see on in the right-hand photograph. Those 2 gimbal points are actually a slide-in attachment. Those 2 points have to be steel because they have to survive repeated inputs and outputs. So there are damping pads between the steel and the magnesium of the fixture. The bottom plate of that fixture is 5 inches thick. The side posts are started out as 8-inch thick blocks, and everything was carved away carefully until we could get that entire fixture to attach to the shaker. The notches in the front have to be there because there are devices on the product that stick down through those notches, and the unit has to be checked out before it's taken out of the fixture, so it has to be powered up. In the left-hand view, this product was purposely blurred. About all I can tell you is it is a defense product, and we do not want that to be shown. You can see that we have our wrenches still laying on top of it from fastening it down. This fixture is very, very touchy. It has an extremely difficult profile with lots of notches and peaks and lots of things going on in the profile. It's extremely noisy. The fixture has to just literally take constant abuse. The interesting thing that we found out is the customer had used the fixture for almost a year and a half and called in one day and said, "We're having problems with that fixture. It's not working anymore." And I said, "Well, let's check out how your product is mounting. Maybe we need to replace the pads that are underneath the steel blocks. Maybe we need to do some other checking, make sure all your bolts are in there. If you don't mind sending me your program, I'll look that over again just in case something's changed." And about 4 days later, they called back and they said, "Never mind." We found out that the product that was inside of it had an internal defect and was broken inside, and that's why it couldn't control. So here's an example of a fixture that's so robust that as soon as the product is no longer okay, the fixture won't control the test. The fixture is extremely heavy, and so is the product. And those two in combination made this really, really difficult to control. When we do fixture design and fixture construction at Thermotron, we try to weld every joint we possibly can. And when we weld those joints, we use a 75-25 rule. What I mean by that is at every joint, 75% of that joint ends up being weld, and only 25% of that is flat surface contact from the original contact of whatever it is that you're welding together. How do we achieve that? In many cases, it machines tapering items so that they meet only at light areas and then filling that all back in with very, very heavy welds. Is it necessary? Not always. But I can't afford to have a fixture come back that we send out in the field. So is it a question of affording a fixture that works or a fixture that doesn't work? And I think I want to always choose for one that works. The other thing that we do is we always machine after welding is completed so that all of our surfaces are true and flat. I've seen a lot of fixtures that were welded together very quickly, sometimes skip welded, not following that 75-25 rule. And I've seen fixtures that were not machined, and I've seen product that gets torqued and fixtures that get bent as they get bolted down to the shaker. And all that was required was to simply surface off the fixture and bolt it back down, and everything changed from a fixture that wouldn't work to a fixture that worked very, very well. Another thing that we look at when we're doing design is we realize that there are 5 times as many bolts required for shear transmission, that is sliding transmission, as are required for compression transmission if the friction coefficient is 0.2. Now, when I say if the friction coefficient is 0.2, what I really mean is if the 2 items being bolted together are metal, pretty much always the friction coefficient is going to be in the range of 0.2. So I need 5 times as many bolts when I mount my product sideways and have my bolts horizontal as when I have it vertical and my bolts are being stretched as it's being vibrated. Now let's talk about material. What should I use? Magnesium, aluminum, or steel? To understand why you should use certain materials. First of all, let's look at the second statement. For the same mass, the cross-section of a beam increases as material density decreases. Let that sink for a little bit because that's important. The lighter the material is that I'm using, the thicker I can make it. Now go on to the next statement, which says that cross-sectional thickness affects resonance because bending modes are inhibited by thickness. So the thicker the beam, the less chance of a bending mode within the beam. And right along with that, the more chance of actually transmitting the vibration through that beam to your product. So the final thing to remember is that the same width beam can be made thicker with no increase in mass if you change the material to a lighter material. So magnesium, aluminum, or steel. Well, let's look at just what that could mean. Let's start with a 4-inch square plate, a 1/4-inch thick steel. And then let's use aluminum and make it thicker just by changing the ratio of the mass. And then we'll look at magnesium. If my volume increases, which it does, from a 1/4-inch thick plate, in aluminum now it's 3/4 of an inch thick, and in magnesium it's almost an 1.1 thick. What I've done is I've changed my first resonance of that chunk of plate. Remember, this is only a 4-inch square plate. It has a first resonance of only 520 hertz. If I'm attempting to run a test to 1,000 hertz and I have my first resonance at 520, I'm probably in trouble. All I have to do is change to aluminum and use the same amount of mass. I'm driving the same mass, so my shaker has to drive the same amount of mass. And I have tripled my resonance. I've gone from 520 to 1470. And if I go to magnesium, I've quadrupled my first resonance. You can see this chart kind of shows you how that all goes. This was all done using ANSYS and just looking at an unbounded square plate, just looking at its natural resonances. There's a graphic of the FEA study. You see that first resonance of the steel. You can see it's bending. The first resonance of the aluminum is bending a little bit differently. And there's the first resonance of magnesium. And you can see the thickness is written on top again. Go back to the steel. It was only a 1/4 inch thick. The aluminum was almost 3/4 of an inch thick. The magnesium was an inch plus thick. Remember that first resonance went way up. The magnesium was 4 times what the steel was. And it didn't have any more mass. Is it more expensive? Yes, I understand that. But I also understand that it's going to be a better quality fixture. In addition to fixture construction, one of the things that's of concern to us quite often is fastener health. Thread life is an issue for all fixtures. You want your fixturing to be used repeatedly, over and over and over. You don't want to be replacing your fixture constantly. You do not want to have to change out the fixture every time it wears out. So you want to make your fixture so durable that it doesn't break down in the fastener locations. Well, fasteners, that is bolts and nuts, are not made to be used repeatedly. I'm going to repeat that. Fasteners are not made to be used repeatedly. I learned this lesson many, many years ago when I took apart my first automobile, and I was told by a mechanic who had a lot more experience than I did that I needed to put new head bolts in before I put that head back on that engine. I didn't listen to him. I had to replace the head gasket in less than 500 miles. You can believe that the second time I put in new head bolts, and I didn't have a problem again. He was right. Fasteners are not made to be used repeatedly. Now, the fastener itself will stretch, but not only that, the threads stretch. And if you look at the graphic in the lower left-hand corner, you can see what happens. You can see there's gaps in the thread as you tighten up the bolt. In bolt nut combinations, the nuts are usually made of a softer material than the bolt so that the nut fails. Well, we're trying to use a fixture, and we have to have an insert in that fixture that a bolt goes into. So our insert has to be of a quality that the bolt can't make the insert fail. So we have to constantly bear in mind that the durability of the insert has to be higher than the durability of the bolt. We do not recommend at Thermotron that you use helical inserts. The biggest reason is a helical insert simply does what's in that lower left-hand corner. It transfers that stretch from the bolt through the helical insert into the material of the fixture. If you use a key locking insert, that doesn't happen. That key lock thread is strong and holds on to that fixture. And now it's time for questions or comments.
All right. Well, thank you so much, Milt. Great job. As I mentioned if you have any questions, feel free to submit them through the chat window to our organizer, Jane Newton. I also want to let you know that a recording of this webinar will be available to you so that you can rewatch it or pass along to any colleagues who are not able to attend. We'll also have some information, contact information on the next slide that tells you if you need more information or we haven't gotten to your question. You can reach out to us and we'll try to answer it there. So if you need to reach out to us, feel free to email us at info@thermotron.com, or you can call us at 616-393-4580, or even visit our website, thermotron.com. All right, Milt, are you ready for your first question?
Sure. Question number one, can you remove the standoffs in a place where the fixture would normally be connected, or build in a buffer zone on the fixture? For example, the middle attachment point on a 3x3 fixture. How does this affect the fixture? Yes, you can remove the standoffs, but in my mind, it's always simpler simply to put a little relief spot in the fixture where that standoff would touch the fixture so that the fixture is away from the standoff enough to stop that from buzzing. It affects the fixture only if, by removing that attachment point, that fixture can bend too easily. So if the fixture is not robust enough to handle the bending that it's going to see during vibration, then you have a problem. But if that fixture is built with enough durability and it's solid and heavy, typically then that's not an issue. Second question I've got is, what is the approximate cost of a fixture? That's a difficult question to answer. Thermotron has sold fixtures anywhere from $30 to $75,000. And we've quoted fixtures even more expensive than that. Fixturing is going to pretty much reflect the product cost. If you have a product that's an expensive product and the product has attachment points in very difficult planes, such as that example that I showed earlier, that fixture is going to be an expensive fixture to build. Thermotron simply passes on these costs to you as a customer if you have us do a fixture. When we design a fixture, we try and design a fixture very, very carefully. We run a finite element analysis on those fixtures. We ask all kinds of questions about your intended use, and we ask all kinds of questions about the product. The more information we get, the lower cost we can make that fixture. If we don't have enough information, often we'll opt for making the fixture so robust that we can't get in trouble even though we don't have the right information. So again, that's an incredibly difficult question to answer, and I've given you a huge range, and I know of fixtures that are even more expensive than that $75,000 I quoted. And that's per fixture.
All right, we have a few more questions that came in.
First one is, does fixture CG affect cross-axis vibration? Yes, it does. In two different ways. If the CG is not on the center line of the shaker, it creates cross-axis vibration because it forces the shaker to literally turn while it goes up and down. And that turns into cross-axis vibration. In addition, if the center of gravity is extremely high above the shaker, you get what's called whipping motion, and the product simply starts to wiggle back and forth. So the goal in a fixture is to try and get the vertical center of gravity as low as possible and get that center of gravity as much as over the center line of that shaker as you possibly can. I've had people ask, how good is good enough? And I kind of go, well, you have to think about how high your test is. If you're trying to run a 80G test on an incredibly light product and an incredibly light fixture, you've got a problem if you're off more than 1/4 of an inch, because you've got incredible overturning moments. So it becomes a difficult question to answer, but it does affect it. How often should you replace the fasteners? My recommendation is to do this. Survey the fasteners constantly. If you're using black oxide bolts, and I would recommend that that would be what you use, I would stay away from stainless steel because stainless steel has a habit of gulling under vibration, and then you have this difficult issue of not being able to get the bolt out of the insert. If you use black oxide bolts, as soon as you see brightness on the thread of the bolts, in other words, as soon as you've seen the black oxide wear off, it's time to replace the bolt. If you want to look a little more carefully, as soon as you see thread deformation, then it's definitely time to replace the bolt. Now, what I would do is I would chart that for a while, and eventually you'll get a pretty good idea of how long it takes for that fastener to show damage in your particular application. And then from that chart, you can make a decision about how often that you can just replace them that often. In my opinion, if you put a bolt in and out of an insert a dozen times, you're at a point where it's time to start seriously thinking about replacing that fastener.
Well, the floodgate's kind of open. We got a whole bunch of questions just submitted, so we'll give Milt a second to review them. But we'll probably have time for maybe 2 more questions or so. We don't want to keep anybody over. But like I said, if you think of something after the webinar, feel free to contact us, and then we'll have a slide showing when we wrap up. And email us the question. We'll try to answer it as soon as we can. Well, now the next question, Milt.
Okay. I've been handed a fairly good list this time, so we'll take them one at a time. How close should the monitor signal be to the control signal? Is there a ratio that indicates your figure is solid enough? I'm not sure I can answer how close those need to be. If your monitor signal is too far away from your control signal, then that means your fixture is not solid, obviously. Now, are you monitoring on your product, or are you monitoring near an attachment point? We would not recommend monitoring on the product. We would recommend you monitor at attachment points. That was one of the other criteria for this particular fixture, is we had to monitor on top of that lower steel plate, which is the second plate down in that block. And there is a drilled and tapped hole for the accelerometer in that plate. So we're attaching an accelerometer to a steel plate, which is not exactly recommended practice, but it works in this application. And that monitor signal and the control signal were fairly close to each other there. We were within plus or minus 2.5 dB, which was one of the requirements of that particular fixture. Sometimes that's not reasonable, sometimes that's not achievable. The concern is, does your product break because you don't have it under control? and because that monitor signal and control are too far apart. And then your fixture is not solid enough. So that ratio is something that you have to think about and you have to determine. And if you know what that ratio has to be, you design a fixture to try and achieve that. And that's what we do when we try and run FEA analysis. We try to look at what the transmissibility is and try and determine exactly how to build that fixture as robustly as possible. Can you comment on fixtures for test of rack mount equipment and use of racks? Let me swallow a couple times first, and then I'll answer that question. I have yet to see a successful test on rack mount equipment when the product was monitored in the rack. Now, there are tests that we have had to run for particular customers that were testing the impact into the rack. In other words, we were given a base acceleration that rack mount, the entire rack of equipment, would see in its final use, and that's what the shaker had to output. Well, that was done by putting the control accelerometer on the shaker, and the goal of the test was that the tested equipment had to survive. It did, and the test was valid. If, however, you expect to control on product inside that rack, you have got slamming and pounding and all of those things going on that I said are not good to do, and you're going to have an extremely difficult time to control. You're going to have so many nonlinearities, you're not going to be able to push energy through. Do you have a rule of thumb for a thickness of a fixture versus UUT mass in order to avoid test fixture resonances between 10 Hz to 2000 Hz? No, I don't have a rule of thumb for thickness. Too much is dependent on the UUT's design and configuration. If I have a tall, thin unit under test and I have to mount it so that its length or its biggest length is vertical, I'm going to have to build a lot more sturdy fixture than if I have a UUT that is laying flat, so its longest length is laying flat on the fixture itself. So too much depends on how the unit under test is, and we tried to design around that. The rule of thumb, remember I went back when I talked about the construction method. We use up that top-down design. That pretty much assumes solid mass from the product all the way down to the shaker table. Then you start carving away where you think you can get rid of material. So there is no such thing in my mind as a rule of thumb because it depends too much on the product and the test. You mentioned matching the real-world attachments, but how do you address real-world stiffness and damping? That's a very good question because that's the kind of thing that's very, very difficult to model in FEA. We seldom know the damping inside of a product because more and more products are built out of composites and other products that dampen so well internally. So we need to have tremendous information. Can we model a unit under test appropriately? Probably not. We try to do our best judgment on the unit under test, and we try to focus on the fixture to eliminate bending modes as much as possible. Damping is more an issue of material. Magnesium is a very well damped material. Steel is not. Another reason to use magnesium instead of steel. You mentioned marine plywood could be used for fixturing. What properties make this a good fixture? Number one, it's damp. It's highly damp. Number two, it does not have internal voids, so it's stiff all the way through, and energy can be transmitted through it quite well up to certain frequencies. You probably can't use marine plywood in a fixture that needs to go to 2000 Hertz, but you could very easily use it in a fixture that has to go to 500 Hertz. is there a typical fixture mass to test article mass? It kind of goes back to the rule of thumb for thickness of fixture. To start out with, if I have a customer that calls in to size a shaker, I typically will say, tell me what your product weighs, and I will triple that for fixture mass and see where we're at on a shaker model that will drive that much mass. Now, I would hope I could get by with a fixture that would weigh twice what the product weighs, but I have had to make it 3 times the product at times. And then the last question, does powder coating or painting a fixture have any effect on performance? If the thickness of the coating is too thick and the coating is too soft or too plastic, yes, it can have an effect on performance. Sometimes that's a desirable effect because it means that the surfaces that are touching each other don't rattle. But typically you want to have any paint or any powder coating as thin as you can possibly get it. What it does have an effect on is the durability of the fixture, especially in situations where there's a lot of humidity or a lot of corrosive atmosphere, such as locations near the ocean. That's where you really want to look at powder coating or painting, because you don't want to have to buy that fixture because it corroded too much. Now, the one place where corrosion is a real issue is where the fasteners touch and where the inserts are put into the fixture. And that's an area where the powder coat has to cover that up so that it does not corrode in that area. But that's a constant issue for performance.
All right. Well, very good, Milt. I really appreciate your time, and I'm sure the attendees appreciate it as well. So we hope that you got a lot of value out of this webinar. As I mentioned earlier, if you still have any questions, feel free to contact us and maybe email those questions to us, and we'll try to get back to you. Also, just an update that we will be sending out an email, I believe, tomorrow that will have a link to the recording of the webinar, so you can review it later on at your own convenience or pass it on to some teammates or colleagues, whatever makes sense. So once again, on behalf of everybody here at Thermotron, thank you for attending, and we hope that you found a lot of value in attending. Thank you much, and have a great day. Bye-bye.